So do we remember how we complete the square? Which means you're going to take some quadratic that looks like this and make it look like this. So knowing what you want it to make it look like kind of gives you the hints for what you need to do. Like this A matches up with that A. You're going to have to factor that out. And you only have to factor it out of the first two because the C value here is going to change, but it's going to change into the K value in the end. So we're going to look at specific examples and see how completing the square is going to help us. Okay? Here are the two things that are important. Your tan inverse integral and your sine inverse integral. They both have square things involved in it. So you get a question like this. 1 over x squared plus 6x plus 10. In your mind, you might think substitution. Maybe I should make my u the bottom. But the problem is the derivative of the bottom is 2x, and you don't have an extra 2x there. So strategy 1, substitution doesn't work. You might think, well, maybe I should use a natural logarithm, but then you have the chain rule, and that's basically substitution problem once again. So what do? We look at what we have, and we want to change the x squared plus 6x into a perfect square. So if I had x squared plus 6x, do you see that if you added 9 to it, it would make a perfect x plus 3 squared? And this one just so happens to work out perfectly that if you add that 9 and subtract the 9, you get x plus 3 squared plus 1. So I could rewrite the bottom as x plus 3 squared plus 1. I have in my mind, right, the integral of x squared plus 1 dx is tan inverse x. I have that in my mind. So now if I make my u x plus 3, my du becomes dx. This just becomes tan inverse of u plus c. And we have tan inverse of x plus 3 plus c. One of the hard parts about integration is the recognition of what technique you should use. So one of the strategies I would say in this one is with the tan inverse and the sine inverse one, you're looking for something squared on the bottom, nothing on the top, just a 1 or some constant. Gives you an idea, maybe I should try a completing the square technique. But really, you have to sort of have all of your techniques available quite quickly. So the purple sheet of all your standard integrals, those have to be well known. So you can quickly look at this and say, this doesn't fit any of my standard techniques. After my standard techniques, then I would go into substitution. Can I use substitution here? And I don't see the derivative in this question. I see a square root, I see an x squared, I think of my sine inverse. So what do I need to do? I've got negative x squared plus 8x minus 15. My sine inverse equation, right? In my head, I have my sine inverse equation looking like this. I'm actually happy there's a negative x squared there. So my question is, can I rearrange this so that it looks like 1 minus something squared? So I look at completing the square. If I take out the negative out of the first two terms, and then I see the minus 8, remember the strategy for completing the square? You always take this middle number, divide it by 2. That tells you it's going to be x minus 4. When you square minus 4, that would tell you you need to add a 16 in there. Why did I also add 16 in red? Can you see it? Because last time we added 9 and subtracted 9. This time we're adding 16 and adding 16 again. Well, this negative sign out front, that would hit that 16. You've actually subtracted that 16. So to compensate, you need to add 16. This is actually comes up quite often in math as an advanced strategy. Can't do something, why don't you add 3 and subtract 3 at the same time? It's like, you mean do nothing? Yes, that is a very important high-level math strategy, is doing something that does nothing, apparently. And that's what the blue 16 and the red 16 are. You're just adding nothing in the shape of adding 16 and subtracting 16 at the same time. But it allows us to change this to negative x minus 4 squared, and I could rewrite this. I probably would have rewritten it with the 1 first right away. 1 minus x minus 4 all squared, and then we can make our u equal to x minus 4, do a substitution, and we've got our perfect sine inverse. So it's going to be sine inverse u, substitute that, and we get sine inverse x minus 4 plus c. So I'm going to get you to try the next one. I'm going to just tell you a couple things about it. First of all, there's a 32 on top. That's just a number. Anytime you have just a number, you could factor that out, put it out in front as a 32. That would get a 1 on the top. Having that 1 on the top, having a squared on the bottom, do you see this as a tan inverse 1? Because there's no square root. See if you can complete the square and get the tan inverse. Well, let's see if you can complete the square. We'll show what it looks like after you've done that. See if there's any other mathematical issues that come up. And if you get this one done quickly, you want to start working ahead. We've got another 3 on the next page to try. I am going to write down that's our goal. If we have that, we can get tan inverse. Checking, did you get x minus 2 squared plus 16? Okay. Do you see that this is going to add another mathematical issue for us? Because in the tan inverse, it's supposed to be plus 1. And we have a plus 16. So how do we deal with that? We need to make that a plus 1, which would mean I should divide that by 16. But if I divide that by 16, I need to divide this whole thing by 16. And if I divide the whole bottom by 16, I need to divide the whole top by 16. Because what you do to keep the fraction the same. So if I multiply the whole top by 1/16 and I multiply the whole bottom by 1/16, what does that do? That changes it to the +1 that I wanted. But do you see that now you don't just have something squared +1? We now have something squared over 16 +1. So I need to also move that 16 into the square. Does that make sense? Like if this whole thing, right now, this is the only thing that's squared. But in my tan inverse, the whole thing needs to be squared. So I need to somehow combine those things into something all squared. Can you see that your 16 is really 4 squared? I could put the 4 in and just have, oops, hold on. If I put the 4 in and make it all squared this way, now I have something matching up. Then I took the 2 that was on the top, I pulled it out in front, so I could really get, and I can put a purple box around this. That really, really matches up. I don't think my boxes have this, so at this point, I would let u equal x minus 2 all over 4, which is the same as x over 4 minus 2 over 4. If I break up that fraction, that would be the inside. The reason I broke it up is so that you could easily see that du was 1/4 dx. Or that you could replace the dx with 4 du. So now taking that substitution, it's going to equal to integral of 1 over u squared plus 1 4 du. That 4 can come out in front, making an 8, right? This is going to be tan inverse of u plus c. My excellence. And again, if you wanted to now, you could take this derivative. This is good to practice your derivatives. I'd highly recommend finishing an integral, taking the derivative, and see if you get the original equation back. But in this completing the square technique, not only do you have a goal, right? Here's like the only thing I think that matches up is the tan inverse, which I need a 1 over something squared plus 1. And we had to do a fair bit of manipulation before it was in the right spot that we could do that substitution. So once again, you have to think you're going to see this question out of context of this lesson. When you see it in the context of this lesson, your mind is already in that idea. This is going to come and you're going to first go through all of your algebra and regular integration things. So you go through all 20 of those and say, okay, it doesn't match up with that. Then you're going to go through substitution. I definitely have an inside function. I have 2x minus x squared, but its derivative doesn't show up in this equation, so I have to rule out substitution. And now I'm going to go to my advanced techniques. It's not a trig identities one because there's no trig identities. It's not, might it be algebraic manipulation? Maybe. So I go through that in my head, cancel that out. And now I finally get to this last technique that we're learning, and say, okay, well, I guess I'm going to try to get this so I complete the square. And it works out really nicely. And you can do the U substitution, but sometimes if the U substitution is so easy, like do you see that U would be x minus 1, and du would just be dx, you probably can go directly to here without doing the U substitution. The last one that we just did, I think definitely still needed the U substitution because it had that extra 4, some extra mental math that needs to be done. But if you can see that your U substitution doesn't do any kind of extra numbers, you can still choose to do it. It's not, it like adds 1 extra line. It's not really that much more work. But if you skipped it in this case, they wouldn't go, oh, we have to take off marks because you've not shown work. That'd be perfectly fine. Okay, try the last two. All right, I'll put up the first one. In the completing the square of the first one, we have some fractions. Should have got an x plus 1/2 squared plus 7/4. That 7/4 is an issue. So I'm going to need to get that to be a plus 1. To get this a plus 1, I'd have to multiply by 4/7. I'd have to multiply by 4/7 on the bottom, and I'd have to multiply by 4/7 on the top. What does that give me? Well, that gives me a bit of a problem because in tan inverse, this has to be one thing squared. And right now, this is the only part squared. So again, some more algebraic manipulation. Square root of 4 is easy. That's 2. Square root of 7. It's easy. It's a square root of 7. We put that inside. And this would definitely be one where I think you might want to go let u equal that inside, which is 2 over root 7 x plus 1/2. Do you see that du, if you distributed that, your derivative is just going to be 2 over root 7 dx. Which means our dx is going to be root 7 over 2 du. So now I have my integral. I could bring the 4/7 on the top out in front. This becomes u squared plus 1. And instead of dx, I would have root 7 over 2 du. For root 7 over 14. Just took that root 7 over 2 and multiplied it by what's out in front. This becomes tan inverse of, and at this point you can actually, like I could write u here, but if you wanted to save yourself some time, you already know that you're going to have to substitute it back. It's just u inside here, so I could take my 2 over root 7 x plus 1/2. Slide this over. and get my final answer. And I find that these ones with completing the square, and especially with tan inverse and sine inverse, like if this was multiple choice, and you started with this, and this was one of your solutions, like, they look so different, don't they? They don't look even remotely the same. Everything in your multiple choice lifetime has told you, if something's so ridiculous, this teacher doesn't know what they're doing, this is not a right answer, I can cancel it out right away. Have you ever had some of those multiple choice questions where your teacher has thought they would try to be funny? And it's like, what's the capital of Canada? And one of the choices is elephant. And you're like, okay, that's obviously not a right answer. This to me looks like it shouldn't be a right answer because it's so different than what that final thing is. So if you got these on multiple choice, for multiple choice, you have options for integration. You can either do the complicated integration techniques and hope it matches up, or you could take all four possibilities and do the derivative of all four and simplify them and see if it matches your original question. Those are both options available. Neither of them seem very quick and easy. That's one we just did. All right. Have you got, yeah, I think you've got, did you get this as you're completing the square? And in your head, you're thinking sine inverse because I see the square root. What's the issue? The issue is the 4. So I'm going to have to take that 4 out to make it a 1. If I take that 4 out, maybe I'm going to, for those of you that like an extra step to see the math, which I think is nice, this is what I would do as my extra step in between here and here. I factor out the 4 to make a 1. If I factor out a 4 to make a 1, that makes this over 4. My next step is I want in the square root 1 minus something squared. So this 4 has to come out. Well, what's the square root of 4? That just becomes 2. If it was an ugly number, if it was square root of 7, I would pull out a square root of 7 out in front. Okay? What's nice about that? That it gives me my 1 all by itself. Now, this part here, right now, only this is getting squared. So I need to move that 4 to get squared as well. So that's going to be a 2. If it was a not nice number like a 7, you would just change it to a square root of 7 inside, all squared. Okay, I would definitely, so now we have that 2 on the bottom, that 2 can come out in front as a 1/2. I have 1 over 1 minus, and this is inside the square root, x minus 2 over 2, all squared. So it has a little bit of stuff in there. If you took your derivative, you get 1/2 dx. Well, technically, right, this is where integration, technically, this is your derivative, du dx. And then with integration, we do this fancy thing where we think of it as a fraction, move the dx over there. I multiply both sides by 2, so I could substitute for my dx. So me personally, whenever I have any kind of number in there, I like to do the U substitution, and it just makes it simpler. I don't make a mental math mistake. You might see that this 2 is going to cancel out with that 2. That works out really nicely. And I'm going to get sine inverse, and here I would substitute back right away. That one actually worked out quite nicely.